multi-million-dollar manufacturing companies operating right now whose entire future relies on a single dusty piece of cardboard.
Yeah, it's pretty wild to think about.
Right, like think about that for a second. You could have this massive cut and sew production room, incredibly skilled workers, highly specialized products, and, it is all anchored by physical paper patterns just hanging on walls or stuffed into overflowing cabinets.
Literally just stacked up in the corner.
Exactly. And if a pipe bursts tonight, or, I don't know, a roof leaks, a company's best-selling product and decades of accumulated manufacturing knowledge might literally dissolve by tomorrow morning.
Just gone. Poof.
Gone. So today we are taking a deep dive into how to rescue that trapped data. We've got some incredible source material today, and our mission is to explore the highly technical what, the why, and the exact step-by-step mechanics of transitioning a manufacturing facility from a traditional, paper-based manual cutting operation into a fully integrated digital production ecosystem.
And, the tension here is fascinating because those paper patterns might actually still work today.
Right, they aren't technically broken.
Right. I mean, a skilled floor worker could pull a cardboard template off a hook and just trace it with chalk, just like they did 20 years ago.
Yeah.
So the problem isn't necessarily the paper itself. It's that the entire manufacturing environment surrounding that cutting room has, it's completely evolved.
Right. The rest of the world moved on.
Exactly. Modern clients expect to send digital files. Upstream pattern departments and grading companies, the people who mathematically scale a single design into multiple sizes, they're operating entirely in the digital realm now.
Yeah, nobody is mailing a large and a medium cardboard cutout.
No, of course not.
Yeah.
And crucially, modern high-speed automated machinery, it cannot read a piece of cardboard.
Right.
So we have to figure out how a traditional manufacturer bridges that gap and adopts digital production without, halting their existing operations and losing revenue in the process.
Okay, let's unpack this.
Right.
Because I want to look closely at the mechanics of why paper is failing modern supply chains. Because relying on paper in today's supply chain is it's like keeping your company's entire accounting system in a single handwritten ledger.
Oh, that's a great analogy. Yeah.
Right. It's beautiful, it has history, but if there's a fire or if you just need to share it with an auditor in another state, you are entirely stuck. The data is a hostage to its physical medium.
It's trapped.
It's totally trapped. If you need to send a paper pattern to a partner facility across the country, you cannot just attach it to an email. You are boxing it up, shipping it, and crossing your fingers it doesn't get bent or lost in transit.
Yeah, and that physical vulnerability is just the baseline problem. But let's look at the actual physics of manual production on the factory floor.
Okay.
Because when an operator traces a physical pattern, we are introducing these tiny compounding human errors.
Like what?
Well, think about the chalk, right? A freshly sharpened piece of chalk draws a very thin line. But at the end of a long shift, that dull piece of chalk might be drawing a line 1/4 of an inch thick.
Oh, wow. I didn't even think about that.
Yeah. Add in the fact that fabric shifts when human hands pull shears through it, or, an operator might hold the cutting tool at a slightly different angle from one piece to the next. The geometry changes ever so slightly with every single cut.
Which means the sewing department is constantly compensating for those 1/4 inch variations down the line. It just slows everything down.
Precisely. And that brings us to the ultimate barrier: automation.
Right.
If a manufacturer wants to scale up and use an automated cutting machine, they hit a wall. Automated cutters do not possess eyes. They cannot look at a chalk line.
They need math.
They need math. They require digital information that mathematically defines the exact geometry of the cut path. And since paper cannot feed math to a machine, we need dedicated hardware to extract the physical shape and translate it into a digital language.
So we need an extractor. And looking at the materials, this transformation relies on 3 specific technological pillars.
Yep, 3 pillars.
The first one is the V-Shoot Digitizing System. This is the entry point. But how does it actually pull the data off the cardboard? We aren't just taking an iPhone photo of a pattern and calling it a day, right?
Oh, far from it.
Yeah.
No, the V-Shoot acts essentially as a highly calibrated overhead scanning environment.
Okay.
You place the physical pattern on the table, and the system uses specialized high-resolution cameras combined with extraction algorithms.
So it's reading the shape.
Right. It doesn't just capture an image. It understands the contrast between the pattern and the background to identify the exact mathematical perimeter. It recognizes notches, those tiny V-shaped cuts along the edge that tell sewers where to align pieces.
Right, the little alignment markers.
Exactly. It maps the internal grain lines, and then the software converts those physical curves into Bezier curves and vector lines, turning a physical object into a precise set of X and Y coordinates.
Okay, so we've successfully trapped the data inside a computer. We have a digital file, which brings us to the second pillar, the velocity wide format plotter. And I'm looking at this step, and honestly, it seems like a contradiction.
How so?
Well, wait, if the ultimate goal is automated cutting, why do we even have a step for the velocity plotter to print a physical marker? Aren't we trying to get away from paper? Have we just invented a very expensive industrial fax machine?
I know. It sounds completely counterintuitive.
Yeah, why are we printing more paper?
And what's fascinating here is that the plotter is actually the unsung hero of this transition. It acts as a critical safety net.
A safety net.
Yeah, because you don't just flip a switch on a Friday and turn a completely manual factory into a fully automated robotic facility by Monday.
That's true. That would be chaos.
Total chaos.
Facilities have mixed workflows. You might have the budget for one automated cutter, but you still have 3 manual cutting lines running your overflow.
Oh, I see.
So the plotter allows you to receive a digital file from a modern client, process it, and print out a perfectly scaled, mathematically accurate paper layout, a physical marker.
And then your manual team can just lay that giant sheet of paper on top of the fabric and cut through it.
Ah, I see. So it prevents the whole factory from grinding to a halt while the team learns the new systems. It's a bridge.
It is a vital bridge.
Yeah.
It also allows floor managers to visually verify a complex layout before, committing a $1,000 roll of fabric to an automated blade.
Right. Measure twice, cut once.
Exactly.
Yeah.
It ensures that engaging with the digital supply chain doesn't suddenly break your existing manual revenue streams.
That makes a lot of sense, and that makes the third pillar much easier to understand. Once a facility is ready, they utilize the Velocity Pro Cut X automated cutting system.
The heavy lifter.
Right. This is the machine doing the actual physical labor. It receives the digital geometry and cuts the material. But I want to unpack the how here.
Yeah.
We mentioned earlier that it requires math.
Yes.
The sources specifically talk about formats like DXF or ISO. What do those actually do in the context of a massive cutting blade?
Well, DXF and ISO files are essentially coordinate mapping languages. When the ProCut X receives that file, it isn't seeing a picture of a car seat or a jacket. It is reading a massive list of commands, telling the machine head exactly where to move on an X and Y grid.
So it's just raw instructions.
Right. It says, move to coordinate A, plunge the blade, drag to coordinate B at this specific speed, pivot the blade 45 degrees, and then move to coordinate C.
Wow. And to prevent the fabric from shifting around while this robotic blade is just dragging through it, these machines usually use intense vacuum systems, right?
They do, yeah. A vacuum table pulls the layers of fabric down so intensely that they literally compress into a dense, rigid block.
It just sucks it all down flat.
Exactly. And the combination of that rigid material hold down, plus the mathematical perfection of the DXF file, it completely removes the human variability we talked about earlier.
So no more dull chalk.
No more chalk thickness, no more tired hands. The digital geometry directly dictates the physical production, down to the millimeter, every single time.
Okay, let's track a specific piece of data through this whole process to see the workflow in action. Let's imagine a manufacturer making high-end marine upholstery, say, the captain's chair for a luxury yacht.
Love that example.
For decades, they've used a cardboard template for the main seat cushion.
Right. So the journey starts by taking that cardboard template and feeding it into the V-Shoot digitization system. The camera fires, the algorithm maps the curves, and suddenly that vulnerable piece of cardboard is reborn as a digital pattern.
And immediately, the vulnerability drops to 0.
Yep.
Because the next step is storing that digital file in a digital pattern library. It gets tagged, categorized, and backed up to the cloud. You can pull it up instantly, search by the yacht model or year, and you never have to worry about a roof leak destroying it.
Exactly. It's safe forever.
But a single pattern piece isn't enough to start cutting, is it? We have to lay it out.
Which requires generating a digital marker. Think of marker making as playing a high-stakes game of Tetris with your fabric.
Tetris. I like that.
Yeah, you take the digital pattern for the seat cushion, the backrest, the armrests, and you arrange them on a digital representation of your fabric roll. The goal is to nest these shapes so tightly together that you leave almost 0 scrap behind.
Right. Minimizing waste.
Right. In the past, Workers did this by physically sliding cardboard pieces around a giant table. Now, algorithms calculate the absolute highest yield layout possible.
And saving even 2 or 3% of fabric on a massive production run, I mean, that translates to huge cost savings.
Massive savings.
Now, once our digital Tetris game is perfected and saved as a cut file, the facility hits a fork in the road based on their capabilities, right?
Yeah, they look at the cutting floor. If the automated cutter is backed up or if they're still transitioning, they route that cut file to the velocity plotter.
The industrial fax machine.
Exactly. The plotter prints the full optimized layout onto a long sheet of paper, which a human operator lays over the marine vinyl to manually cut.
Or, if the floor is ready, they skip the paper entirely. They send that cut file straight to the automated ProCut X.
The vacuum table activates, the blade drops in, and it executes the geometry perfectly.
So regardless of which path you take, you arrive at the final destination. The actual cut production components, perfectly shaved and ready for the sewing team.
It is a totally seamless loop. But, a facility manager listening to this might feel completely overwhelmed.
Oh, for sure.
Implementing the V-Shoot, the plotters, the automated cutters, the digital libraries, it sounds incredibly disruptive. Ripping out tables to install vacuum cutters could stop production for weeks.
And that brings up the 5-phase progressive implementation plan outlined in the materials. You don't actually walk in on a Monday and unplug the entire factory.
No, definitely not.
You start behind the scenes. Phase 1 is simply digitizing existing, frequently used patterns. You leave the cutting floor entirely alone. Your workers keep cutting with cardboard while someone in the back room starts feeding those heavy hitters into the V-Shoot.
Right. And once you capture those assets, phase 2 is organization. You build out that digital pattern library. You establish naming conventions so a worker can type in a style number and immediately find the exact revision they need.
So you are getting your digital house in order without disrupting a single physical cut.
Exactly. Then, phase 3 is where you start participating in the broader supply chain. You begin receiving digital markers from outside clients or grading services.
Right? No more cardboard in the mail.
Right. Instead of asking clients to mail you cardboard, you say, just email me the file. You route it to the velocity plotter, print it out, and hand it to your manual cutting team.
And by doing that, your floor workers get used to interacting with optimized digital layouts.
Yeah, it builds confidence.
Yeah.
And once that comfort level is established, phase 4 introduces the heavy machinery. You bring the ProCut X online, you start feeding those exact same digital files directly to the automated cutter instead of the plotter.
Which leads right into the final phase, phase 5, full integration. The process becomes a repeatable daily reality. A file comes in, it gets nested, and it goes straight to the cutter. The company modernizes progressively, generating revenue the entire time.
Exactly.
But we need to address a massive hurdle here. We keep talking about editing digital files, nesting patterns, and mathematically scaling sizes. That requires incredibly powerful enterprise design software, massive CAD programs like Gerber, Lectra, or Optitex.
Oh, yeah.
For a mid-sized cut-and-sew shop, licensing that software and hiring specialized CAD engineers is a massive financial barrier, isn't it?
It is a barrier, but it is not a dead end. If we connect this to the bigger picture, this is where the concept of the distributed digital production workflow completely changes the game.
Okay, tell me about that.
Well, a manufacturing facility does not actually need to own enterprise CAD software to reap the benefits of digital cutting. They can outsource the upstream complexity.
So they essentially chop the process up among specialists.
Exactly. It forms a multi-company ecosystem. A designer might sketch an idea. They send that to a dedicated pattern bureau whose sole job is to use high-end CAD software to draft the initial digital pattern.
Okay.
That bureau then sends the file to a grading service. Grading is the highly complex mathematical process of taking a medium-sized pattern and scaling the proportions up for an extra large or down for a small, ensuring the armholes and necklines adjust correctly.
Wow. Then, that graded file goes to a marker-making service. Those are the Tetris experts who use high-powered algorithms to squeeze every inch of yield out of the fabric layout.
Spot on. And finally, the marker-making service emails the finalized production-ready cut file to our manufacturer.
Ah, so the manufacturer just gets the finished product.
Right. The manufacturer doesn't need Gerber or Lectra. They just need the software to receive the file and tell the ProCut X to start slicing. They outsource the digital engineering so they can focus 100% of their energy on physical production and assembly.
That completely democratizes the technology. A local upholstery shop can run the exact same digital workflow as a massive aerospace manufacturer.
Exactly.
And we really should talk of the sheer breadth of industries this applies to. When people hear cut and sew, they naturally think of traditional apparel or fast fashion.
Right. But the underlying geometry doesn't care what material it is cutting.
Yeah.
This exact process, digitize, nest, plot, and cut, is the backbone of furniture manufacturing. From couch cushions to intricate upholstery panels, it is used heavily in automotive interiors, cutting the precise shapes for leather seats, headliners, and door panels.
We mentioned the marine upholstery for yachts earlier, but it also extends to aerospace soft goods.
Oh, heavily.
The interior acoustic panels and seating in commercial aircraft rely on this exact digital precision.
And you see it in military and protective textiles, where, a quarter-inch deviation in Kevlar tactical gear could literally be catastrophic.
Wow.
It applies to industrial filtration fabrics, massive canvas awnings, and outdoor tents. If a product starts on a roll and needs to be shaped for assembly, this workflow applies.
Which brings us to the tangible return on investment. The technology is fascinating, but, a business owner wants to know the actual impact on the bottom line. Let's look at the marine vinyl example again.
Right. If a human operator is manually cutting a $5,000 roll of specialty marine vinyl, a momentary slip of the shears, just a simple human twitch, can ruin an entire panel.
Ouch.
Yeah, that is a massive material loss. The digital workflow, assuming your source files and machine calibrations are correct, provides unmatched repeatability. It eliminates those manual transcription errors entirely.
It also provides incredible labor scalability. If your manual facility gets a sudden order for 10,000 units, your only option is to hire twice as many cutters, buy twice as many tables, and try to manage the chaos.
Good luck with that.
Right. But with an automated cutter, you simply run the machine for another shift. You scale the output of the equipment without a linear increase in manual labor costs.
And don't underestimate the physical space reclaimed either.
No, right. The cardboard rooms.
Going back to that room we visualized at the beginning, the one overflowing with cardboard. Once you digitize decades of patterns into a secure server, you can literally throw away the cardboard.
That's gotta feel good.
Oh, it does. You reclaim thousands of square feet of physical factory space. You can turn a dusty, dead storage room into an active, revenue-generating production line.
You also drastically accelerate your communication speed. We talk about the vulnerability of mailing patterns. In a digital ecosystem, an automotive client in Detroit can finalize a seat design at 9:00 a.m., email the DXF file to a manufacturer in Texas at 9:05 a.m., and the automated cutter can be slicing the leather by 9:30 a.m.
It's just instant.
It really is. And if we synthesize this entire journey, it becomes clear that moving from paper to a digital ecosystem is not just an equipment upgrade. You aren't just buying a fancier pair of scissors.
Definitely not.
It is a fundamental identity change for a business. It is the evolution from isolated, vulnerable manual processes into a networked, digitally enabled production facility. It is the leap that allows a legacy manufacturer to survive and thrive in a modern supply chain.
It is a complete paradigm shift.
Yeah.
And, when you look at the scale of this transformation, it leaves us with a really profound implication for the future of manufacturing.
How so?
Well, we are talking about extracting decades of physical, human knowledge, millions of perfectly fitted patterns, nuanced curves, and historical adjustments from across aerospace, automotive, and apparel, and converting it all into pure digital data.
Right.
Once all that geometry is digitized and stored in vast searchable libraries, well, how long will it be before artificial intelligence systems are let loose on that data?
Oh, wow.
We are rapidly approaching a reality where AI can analyze millions of past successes to automatically generate, grade, and optimize flawless new patterns from scratch, without a human ever touching a piece of paper or even opening a CAD screen.